And what this one focuses on is when you have like an overall process that occurs in more than one step. So you're starting with your starting material in the one reaction, but then your final product is actually maybe one reaction down or two reactions down. I mean, it's a series. So basically what you have to realize is that each reaction you're doing, there's a desired product that you're making, and you're taking that product and you're putting it in the next reaction. You do have to take into account if things aren't 100%. So each reaction would have its own percent yield, and you would have to take that into account. So we're going to look at two examples, one where you're going forward, one where you're going backwards, and that's it for sequential. All right, so sequential reactions are really easy to tell because there's more than one reaction. Like, it's a kind of a dead giveaway. And this is a reaction of how to make nickel carbonyl. Nickel carbonyl is one of the most poisonous chemicals. It's a couple parts per billion is enough to start making you ill and eventually die. So obviously this is not an easy one to make. This is one way you could theoretically make nickel carbonyl. So we want to calculate how much nickel carbonyl could we produce if we had 75 grams of carbon. So you can see this is our starting material up here, and what's different about this reaction is what we want, the nickel carbonyl, is not even in the same reaction. So whenever you're doing a sequential reaction, you have to find bridges, and bridges are a product in one reaction that are then a reactant in the next reaction. And basically, this bridge, this carbon monoxide, is the reason we did the first reaction. We took our carbon, we made carbon monoxide, and then that's what we're using in the next reaction. So it has to be a product in the one reaction and then a reactant in the next one every time. And what that does is it gives you where you're going to in the stoichiometry problem. So the stoichiometry problem starts off like normal. You have 75 grams of carbon. So the first thing you do is you divide by your molar mass to get into moles. And then what you do here, your mole ratio is from what you're given, the carbon, and you go to that bridge. So you can see here, I have 1 mole carbon, and then on top is the 1 mole carbon monoxide right here. Once you've done that, what you have to assume is that however many grams of carbon monoxide you make here, you're going to use that down here. So what you can basically assume is that whatever this carbon monoxide is, this many moles of carbon monoxide is also going to be this many moles of carbon monoxide. And what that allows you to do is it's like, oh, I forget the name of that game, Chutes and Ladders. Like, you slide on down, and this becomes this. So what that allows you to do then is go right into another mole ratio, and you can see here, now we're doing this carbon monoxide one, so we have 4 moles of carbon monoxide, and then we're doing this, the thing we ultimately want, the nickel carbonyl over here. So you can see there's 2 reactions, and we have 2 mole ratios here. And then the last thing is just normal stoich, where we look up 1 mole of nickel carbonyl and its molar mass. So you do your math. And if everything is 100%, you would get 267 grams of nickel carbonyl. Say down here, this is just an extra one. Say step 1 was 100% yield, but say step 2 was only an 83% yield. So what you would do is each percent yield, you have to take that into account. So the 267 grams for the first one, it's just 100%. So that's good. And then you'd have to figure out, well, what's 83% of that 267 for the second one? So you would see you lose a significant amount from percent yields. Say the first reaction had a 90% yield, and the second reaction had an 80% yield. You would have to do that for both of them. So you'd have to take your answer times the 0.9, and then you'd have to take that answer times your 0.8. So you just have to really watch out for percent yields on these, because they can really decrease the amount of product that you're making. So last one on sequential is how can you go backwards? So what they did here is they took hydrogen and they decomposed water, and they got hydrogen gas and oxygen gas. They took that hydrogen gas and reacted with chlorine gas, and they made some hydrogen chloride. The problem is they don't know how much they started with. They forgot to write it down. So it's a little kind of weird because we're going backwards. But we have hydrochloric acid, and that's what we know. We have 84.2 grams of hydrochloric acid. And you still need to look for the bridge the normal way. If you look at the first reaction, we have hydrogen as a product, and we have hydrogen as a reactant in the next one. So that's our bridge, you can see here. And once we have our bridge, we can do this. So we have 84.2 grams of the hydrogen chloride, and we divide by its molar mass, the 36.5 grams from the periodic table. And so we're right here. Now we have to go backwards, because this is a kind of a backwards problem, doing our mole ratio. So we have to go from our hydrogen chloride to this hydrogen right here. So you can say we have 2 moles of hydrogen chloride, 1 mole of hydrogen. Remember, the bridges are kind of like, you can just switch between the two. So once we've done this one, we can immediately slide up and do a mole ratio from this hydrogen one. So you can see there's 2 moles of this hydrogen to 2 moles of water. And then since we want water, we just look up our molar mass of water for this guy. So assuming 100% yields, we would have exactly 20.8 grams of water that would have had to break down for this one for it. So remember, sequentials, you are definitely easy to tell that they're sequential because there's more than one reaction. And the most important thing is that you're looking for the bridges so that you know where your mole ratios are going to be.